All right, welcome. This is Module 11, Chapter 8. This is Part 1. And so now we're going to talk about basic concepts of chemical bonding. Right? And so we can start off talking about that two atoms or ions are going to be held strongly together by different types of chemical bonds. Okay? And there's really three types of chemical bonds, which include ionic, covalent, and metallic. Okay? The ionic chemical bond is just an attraction between two oppositely charged ions. So this would be like a sodium ion and a chloride ion that are attracted to one another. A covalent bond are molecules which are formed by sharing of electrons between atoms, and this is going to be something like a water molecule. Okay, and we can see that down here in the bottom. And then the last is metallic, which is just metals floating in a sea of electrons, so the electrons are delocalized. We won't talk about these as much. We're really going to focus on ionic and covalent in this chapter. So in all chemical bonds, electrons are either going to be shared or transferred between atoms in a chemical bond. And these electrons which are involved in bonding are what we call the valence electrons, okay, because they occupy that outermost shell. And we can see that in these examples where boron has 3 valence electrons, silicon has 4, and antimony has 5. And so a simple way of showing these valence electrons rather than having to draw out all these structures was developed by G.N. Lewis, okay, and it consists of writing the element's chemical symbol and then surrounding that by dots for each valence electron, okay, and these are called Lewis structures. So sulfur has 6 valence electrons, so it has 6 dots surrounding it, where carbon has 4 valence electrons, and therefore it has 4 of these dots surrounding it. All right, and so dots are really just placed on the 4 sides of the symbol, okay, so we can write at the top, the bottom, and the right and the left, okay, and each side we put 2 electrons, okay, because the outer valence shell can only hold a total of 8 electrons, so we can put 2 on each side, and we try to spread those out as much as possible, and it's preferred to add basically the way it's shown instead of on 3 sides, okay, so we could put all 4 electrons on just 2 sides, but it looks better this way, and so that's kind of why we do that. Okay, so you should practice drawing Lewis structures, and we'll talk about that a little bit more during this part. So atoms often gain, lose, or they'll share electrons to achieve the same number of electrons as the noble gas closest to them. Right? Noble gases are non-reactive due to their high ionization energy and low affinity for additional electrons, and they all have 8 valence electrons. Okay? And so basically atoms are always wanting to obtain that 8 valence electrons. Now if you remember, we talked about the electron configuration for ions, and we removed electrons from the subshell with that highest value of n, okay, principal quantum number. Now you have to remember that there's always an exception to every rule, including the octet rule, okay, and so transition metals are an exception to the octet rule. Transition metals will lose s electrons first, and then they'll go and lose their d electrons, only after all those valence s electrons are gone. Okay, and so here's some example Lewis symbols for some different elements, and you should practice drawing those as well. So now we can actually take a closer look at the different types of chemical bonds, and the first one we're going to talk about is ionic bonding. All right, so when sodium reacts with chloride, okay, it has a very violent reaction that takes place. Okay, and so based on the concepts back in Chapter 7, we can see that sodium can basically lose an electron, okay, because its ionization is very low. So if we look at the ionization energy, we can see it's only about 496. Chloride would like to gain an electron since it has a very negative electron affinity, right? And so in this reaction, an electron is lost from sodium, okay, we lose that electron, and the electron is then gained by the chloride, and so we form an Na+, okay, and a Cl-. Okay, these are oppositely charged ions that can be attracted to one another, and now they're both very happy because they have an octet of electrons. Okay, and so they form what's called a lattice, and this is a lattice. So the loss of an electron from an atom is always an endothermic process, as evident in the ionization energy. Okay, the gain of an electron by chloride is exothermic, and it releases 349 kilojoules per mole. So what you would believe is that we could take these numbers, add these up to determine the overall energy of the reaction. Okay, but if you add those up, the reaction is endothermic. It's only 147 kilojoules per mole. But of course that's not the case because that would make life easy. So calculating the energy just by adding these together is assuming that the atoms are very far apart, they'll never interact with one another, but we know that's not true with ionic solids. Right, so one of the things you should note also on this slide is that basically here we can show the Lewis structures reacting together. So sodium, which had 1 in its valence electron, now donates that to chloride or to chlorine, right? So that forms 8 here. Sodium then also has 8 in its last valence shell, okay? Just gave up the 1 extra it had in, whoops, sorry. And so that's how you get the Na plus because it gave up an electron, and Cl minus lost 1. So ionic compounds are stable due to the attraction between these oppositely charged ions, okay? And the attraction then brings those ions together, it releases energy, and it causes these ions to form this lattice, okay? And this stability can really be expressed with the term lattice energy. So the easiest way to think about lattice energy is to picture that you're in the middle of the lattice and you're trying to spread out the ions as far as possible, okay? The energy that's required to do so is called the lattice energy. So for sodium chloride, we can look this up, which has already been calculated, which is 788 kilojoules per mole. Thus, it's highly endothermic, and it requires a lot of energy. Okay, but the reverse process of bringing those ions together is highly negative and exothermic. Okay, and so this actually holds true for many ionic solids, and there's just a reason for these high melting points. All right, and so to calculate the lattice energy, if I want you to calculate the lattice energy of this ionic bond, you would need the distance between the ions and the charge of both ions, and then we can just use this equation, which is the lattice energy is equal to a constant, which is 8.99 times 10 to the 9th, and I would give you that. And then you put the charges of each ion and divide that by the distance. Okay, that's pretty much it. The second type of chemical bond that we can talk about now is covalent bonding. Okay, that is sharing of electrons. So in covalent bond, there are attractions between the electrons and the nuclei. Okay, so there's some you have your electrons, you have your nuclei. There is an attraction between those two. Okay, but there's also a repulsion between the electrons themselves, right? So these two electrons are actually repulsing one another, as well as the nuclei. These two nuclei are kind of pushing away. So if we think about hydrogen, okay, as an example, we can think of that the electrons are repelling one another, the nuclei repel one another, but then the nuclei and the electrons are attracting one another, right? So this is a good picture of just picturing this with the electrons pushing against one another, the nuclei pushing against one another, but at the same time, you have the nuclei and the electrons being attracted to one another, okay? And so the molecule is stable as H2, hydrogen gas. So that means this attractive force between these must be greater than the repulsive forces. Okay? And so the attraction between the two atoms results in an electron density cloud, which is shown here, okay? Which is just concentrated between those two nuclei. Okay? So the electrons kind of get pushed together. So sharing of electrons between two elements really constitutes a covalent bond. Okay? And there's really 3 types. So a single shared electron pair we can just call a single bond. 2 electron pairs that are shared is a double bond, and sharing of 3 pairs of electrons is a triple bond. Okay? And so we can actually look at this with these different Lewis structures. So hydrogen, which has 1 electron, we show hydrogen has 1 electron, these come together, those kind of interact in this cloud that we just showed back here of electron density. Okay? And so we just show a single bond for those single pair of electrons being shared. Now you could have carbon and 2 oxygens come together, and what happens is these actually share 2 sets of electrons, okay? And so we show the double bond. Or with nitrogen, it shares 3 sets of electrons, so we have 3 bonds, okay, a triple bond. So generally, the more electrons that are shared, the shorter the bond length and the stronger the bond. So now we can talk about bond polarity. So bond polarity is just a measure of how equally or unequally the electrons in a covalent bond are shared. Okay, there's really 2 extremes to understand bond polarity. One is the nonpolar covalent bond, which is if you think of F2 or H2 like hydrogen gas, you can see that basically they're equal, right? The electrons being shared equally, and we can kind of see that with these color diagrams. The second extreme is a polar covalent bond, which means one of the atoms in the bond exerts a greater attraction for the bonding electron than the other atoms. Okay, and so the most extreme case you could think of would be sodium and chloride, right? Chloride really wants that electron. Sodium kind of just hanging on to it barely. So there's a really big difference there. Okay, there's little sharing that occurs, and so that's actually an ionic bond. Okay, and in the example we can see here we have HF. Fluorine really wants that electron, and you can see that being pulled with that red color. So to understand bond polarity a bit more, we really need to understand what electronegativity is. Okay, electronegativity is the ability of an atom in a molecule to attract an electron itself. It's kind of like a tug of war between those two atoms in a molecule. So the electronegativity of an element is related to its ionization energy as well as electron affinity. So a very negative electron affinity and a high ionization energy means you're going to have a highly electronegative atom. Right, and so you should know the trend that electronegativity increases from left to right and from as you move up in the different groups. Well, the difference in electronegativity between two atoms can really help us gauge the polarity of the bond between those two atoms. Okay, the greater the difference in electronegativity between two atoms, the more polar the bond. The farther they are away on the periodic table, the more polar that bond is. Okay, and the farthest are going to be ionic bonds. So you may or may not be given these different values for electronegativity, but if you know that general trend that we just talked about, then you should be able to predict the type of bond and the differences in electronegativity. So these polar molecules actually experience what's called dipole moments. Okay, these dipoles mean that one atom of the covalent bond has a partial positive charge and the other has a partially negative charge. Okay, and we can actually indicate this by either drawing, if we have here we have HF molecule, right? So the fluorine is more electronegative, it's going to pull that electron, and so we can actually draw this arrow above that with this little like plus symbol, plus whichever one's more positively charged, and that shows which way the electron's pulling. Okay, we can also write that this hydrogen is partially positive while the fluorine is partially negative. Okay, the question that should come up is, well, how can we quantify the polarity of a molecule? Well, in order to quantify this, for a nonpolar molecule, the dipole moment is 0, right? There's no charge separation. However, for a polar molecule, we can actually calculate the dipole moment using this equation. Okay, and so Q is just the charge measured in coulombs. Now, if you remember, a lot of times we talk about +1, -1 charge, but we need to convert that to coulombs, and 1 coulomb, or +1 charge is equal to 1.6 times 10 to the minus 19th coulombs. Okay, R is just the distance measured in angstrom, and we should know that conversion. Okay, and so basically we can then calculate the magnitude of that dipole. So that actually concludes, sorry about that. That actually concludes part 2. And then we'll pick up with the Lewis structures and drawing these, which I really encourage you to make sure you practice. So see you in part 2.